questions are asked to the Q&A chat box, and then for extra discussion and questions you will have that we will not have time to address live, you can use the plenary Slack channel. Today we will start with the inaugural edition of the Jocelyn Bell Burnell Inspiration Medal. With this medal, the European Astronomical Society wishes to recognize astronomers of all career stages whose contributions goes beyond scientific research. The name of the prize, Jocelyn Bell Burnell Inspiration Medal, has been decided by the EAS Council after consultation with the EAS membership and is being awarded for the first time in 2021 and will then be awarded in alternate years. Presenting the medal to the winner, it is my great honor for the second year in a row to introduce Jocelyn Bell Burnell herself. She is a role model for generations of astronomers, not only because of her outstanding contribution to science, but also for her commitment to making astronomy more inclusive and equitable. Jocelyn, the floor is yours.
Thank you, Sara. Thank you to the EAS for naming this award after me. I am a curious mixture of pride and embarrassment, and the balance between these shifts like a spectral line in a binary system. I won't say where I am right this second, but thank you indeed for that. It's very great pleasure today to be introducing the first winner of this medal, Mirjana Povic. Mirjana has had a rather special career. She's currently an assistant professor at the Ethiopian Space Science and Technology Institute, and alongside that, a lecturer at the Mabaro University of Science and Technology in Uganda. She's been working for more than 10 years on the development of astronomical science and education in Africa. She received notable awards in 2018 from Nature and in 2019 from the Serbian government. The award this year is for her work on developing astronomy, science, and education as a route out of poverty and to improve the quality of life for young people in Africa. I'm very happy to award this to Mirjana, congratulate her and wish her all the very best for the future. And I'm not sure if folk have seen the medal certificate, so I'll try holding it up. Hard to read perhaps, but there is a wonderful certificate that comes with this.
It can be shared, but yeah, thank you. Go ahead, Jocelyn.
Thank you very much for sharing that. Congratulations again to Mirjana, and I'll hand over to you now, Mirjana, to respond.
Thank you very much, Professor Jocelyn Bell. It is really an honor to be introduced by you, and thank you very much. Also, you've been an inspiration for so many of us during our professional career, for all your contribution to the science and to the society as well. So thank you very much. And I would also like to give my thanks to the European Astronomical Society for giving this very first award for the work that we are doing in Africa for the development of astronomy and science. So saying that, this talk will be dedicated to how through astronomy we can contribute to the Sustainable Development Goals. And I would like to start the talk with this dedication that it's dedicated to all people who in one way or another contributed to the development of astronomy and science in Ethiopia and Africa, and to all of those who will continue doing so in the future. I have to say that over the last now almost 15 years since I started the very first time my volunteer work in Tanzania and Africa, I was extremely lucky and privileged to meet so many people and to work with so many colleagues across the African continent who day to day, despite all challenges, are with their big vision, working on the development of education and science in their countries and then across Africa as well. And without them, this talk today would definitely not be possible. I was also privileged to see how astronomy is really becoming one of the emerging fields on the continent, and to have possibility to participate in all of these activities as well. So when we come to the sustainable development goals, I have to say that across all of these more than 10 years, the journey was not always easy, and it was also not always clear how through astronomy we can really contribute to the benefit of our society. But nowadays I really don't have doubts anymore, and even I dare to make the talk like this, where we can start speaking about how astronomy can contribute to the sustainable development goals and science in general. I think in that aspect we really have to shift a bit from what for a long time were short-term measures to fight poverty, and to switch to the long-term measures and possibilities to fight poverty in a sustainable way. I think the new European African Union strategy for science and innovation development is one of really good and important steps in that aspect. And I would like to mention these fields here: education, science, technological development, innovation, that are really key tools to fight poverty in the long term. And we can also not achieve sustainable development goals without empowering girls and women, 50% of our population, in all aspects of our society, including science. The problem of poverty that we have in Africa and across the world is not a problem only of African countries and other countries that are exposed to it, but the problem of all of us, independently on where we are, because we don't have another world, and we all shape this world and how this world will be in the future. So I think that independently where we are in one way or another, we can contribute that in future we can make our world a better place, being involved in one of these fundamental aspects of our society that I mentioned here. And astronomy really shown to be important tool for development. Here I will just mention 4 important points. There are many others. First, we know that astronomy is one of the most multidisciplinary sciences. It's related with all fundamental sciences, but also computer sciences, engineering, material sciences, and also humanities and social sciences like anthropology or ethnology. So it means that through astronomy, we can really benefit to the development of all of these fields that I mentioned. Every time that we do outreach or education activities, we also see how astronomy is really a powerful tool for promoting education and science. And I always like to give an example of working with the street children. And from my experience in Tanzania, in Rwanda, Ghana, South Africa, with street children, who, when most of them are out of the educational system and it's very hard to bring them back, every time we start speaking about astronomy, you will see all of their attention being there. We also know that astronomy is a very powerful tool. It's one of the leading sciences for bringing strong technological developments and innovation. Every time that we have a development of the new generation telescopes or new instruments, we are really speaking about strong technological development that then has application in many other aspects of our society. And also we can hear more and more speaking about astronomy for diplomacy and peace, and we have SKAO as a great example of promoting peace and strong collaborations in a long term. We saw the importance of the digital transformation, digital revolution in which we are currently now during the COVID pandemic. And it is just to remind us how astronomy actually contributed to this digital revolution through the development of the idea behind Wi-Fi, then also through the grid computing, satellite communications, contributing to the CCD development, and through all of these to the computing, communication, GPS system, imaging that are fundamental parts of the nowadays digital revolution. And we also know that through the large data sets of galaxies, stars, astronomy is one of the fundamental fields that contributed to the big data science, and in future through the SKA revolution, where we expect around 100,000 times faster flows than what we have nowadays regarding data, we can really expect even larger contribution to the next digital and industrial revolution. So if all of this is a fact, and many countries actually contributed, developed countries contributed to astronomy to their social economical benefit, then the question is really why African countries cannot do the same, especially taking into account the huge potential that Africa has for astronomy development. First, through the young population that is there. We have so many energetic, very motivated and very inspired people who can really contribute a lot to the development of the education, science, technology in the future and currently. And also, if we remind that dark skies are still one of the African natural resources that open path to the development of SKA, and hopefully it can open path to many other future projects, we can really see the potential of Africa for the development of astronomy. We can remind us the case of Chile, Canary Islands in Spain, and South Africa, where these countries, through their dark skies, managed to benefit in terms of their social economical development through all the science development, access to the first-class data, and also development of the both public and private high-tech and IT sector in the countries, and through different employment opportunities as well. So we can say that it's really time for Africa. We don't really have a justification anymore to ask questions like why African countries shall invest in astronomy or in space science if there are still so many different challenges that the continent, the different countries in the continent are facing. And this idea becomes really a continental initiative. So this is example of the African Union vision, where through the post-2015 development agenda, space science, geospatial technologies, and then astronomy as well have been recognized as important tools for achieving sustainable development goals. Then also here you can see that different countries are working on the infrastructure development, development of the observatories. We will give few words later on regarding that. So it's becoming really a vision, continental vision, and vision of many governments. We now have African Astronomical Society that has been re-established in 2019 and became very vibrant and dynamic society, having currently every time stronger connections with the European Astronomical Society as well. And the aim of AFAS is really to be the voice of astronomy in Africa and to contribute to addressing the challenges faced by Africa through the promotion and then advancement of astronomy. And here you can see the list of different continental initiatives that are there. Many of them are still focused on the human capacity development, trainings, including the International Science Program in Sweden. DARA is doing an amazing job regarding the human capacity development in radio astronomy. We now have, since recently, the African Initiative for Planetary and Space Sciences. A lot of work has been done on the human capacity development through SKA, ABN, the NASP and AIMS in South Africa. We also now have African Network of Women in Astronomy that I will mention a bit later. OID really played a crucial role in development of astronomy over the last 10 years. We also now are starting with the African Strategy for Fundamental and Applied Physics that I will also mention a bit later. And then I would also like to mention Materna, the 5A initiatives that have been suggested for the European funding, and hopefully will get the chance to be accepted in the next call. I will now mention a bit Ethiopia because I will use it in the second part of my talk quite a lot as an example. So Ethiopian government established in 2016 the Ethiopian Space Science and Technology Institute, and in 2014 Entoto Observatory and Research Center. And I was lucky to really participate actively in the development of the institute from the very beginning. The motto, you can see it here, of the institute is that we explore the universe for the benefit of our people. And the vision that the institute has and my colleagues is that really through the space science and technology, including astronomy, we can improve some of the main challenges that Ethiopia is facing in terms of the social, economical status, but also the environmental difficulties. Here you can see different departments that we have, including astronomy, astrophysics, where I'm working. And I would like also to mention that the EAS STI is also hosting the East African Office of Astronomy for Development with my colleague Alemi Emamo, who is really working a lot on promoting astronomy within the region. So how astronomy can contribute to achieving sustainable development goals in Africa will be the second part of my talk, and I will go through different sustainable development goals and give different examples using on one side the work that we are doing in Ethiopia and East African region, and on the other side also the work that we are doing across the continent. And I will also mention different initiatives, unfortunately not all because the time is limited, but there is really a lot going on. So the very first and I would say really significant contribution of astronomy to the sustainable development goals is regarding SDG 4 and the quality education. And when we come to Ethiopia as an example, how we can really contribute in a long term to this sustainable development goal, when, well, the first thing is through the postgraduate program that we are running in 4 different fields. Astronomy is one. So we are now training the very first master PhD students in astronomy. You can see here the numbers of the students who graduated, those that are currently under their studies at the astronomy astrophysics department. And I would like to mention that all of our students are actually already attached to some of the public universities. So once they finish their studies, they will go back and continue teaching many other students. And in this way, we can directly contribute to to improving the level of higher education in Ethiopia and also in East African region, because from Ethiopia, we are also giving a strong support to the East African region, because the similar programs are running. However, the number of qualified people is still limited. So we help through the lecturing and student supervision in Rwanda, Uganda, Tanzania, and Kenya, also in collaboration with South Africa. Through the network of astronomy school education with my colleague Rosa Maria Ros from Spain, we organized, and then with in collaboration with our colleagues from different African countries, especially in East African region, we organize different teachers trainings where we are not only teaching astronomy, the teachers, but we also teach how to teach astronomy by using different recycled materials and making small experiments for showing different physical, astrophysical laws. And then a lot of work has been done really continuously in terms of education, outreach, public awareness. So either through the direct school visits, either through the children, students visiting the Institute and Entoto Observatory. And I would like to mention that only in 2019, before the COVID started, we had more than 10,000 students and children visiting the Entoto Observatory and being inspired with astronomy. Some other examples across Africa, similar as in Ethiopia, now the postgraduate programs have been established in many other countries. Then through the AFAs, the outreach education committees are becoming very active to bring people together. The fact that there is basically public awareness now going all across the continent is also shown through the large number of different astronomical amateur societies that here on the map you can see more than 70 societies. And then again, really strong support has been provided for the human capacity development through different initiatives that I already mentioned previously, including DARA, ISP, and NASP. When we come to another contribution, important contribution of astronomy is for the SDG 5 for gender equality. I will mention two initiatives, STEM for Girls in Ethiopia, that we started in 2019 in collaboration with my colleagues from the Society of Ethiopian Women in Science and Technology, where we are going and interacting directly with the secondary school girls and their teachers by bringing women that are professional in some of the fields of STEM and working on the role modeling that is extremely important. Here you can see the example of the activities in one of the boarding schools for the girls in Ethiopia, where after the very first activity that we had there, these girls formed a space science club because they were really inspired with astronomy. I'm also happy to—
5 minutes. 5 minutes.
Thank you, thank you. I'm also happy to mention that now we have the African Network of Women in Astronomy that has been launched recently with the aim to bring together all the women who are working in astronomy on the continent. You can see the coordinating team here. And we now have almost 90 members from 30 countries. And I would like to mention that the majority, more than 80% of our members are actually early career researchers, so just MSc, PSc, PhD students, which means that networks like this are really important for supporting these young women and for making sure that they really remain in science. So what do we need next? And what is also one of our dreams is to really have the Center of Excellence in Africa for training young women in astronomy, but also space science, data science, and related fields. First, because these are really some of the emerging fields in Africa and in the center of the future digital industrial revolutions, and because we need young women to be in the center of these developments and to serve as role models. When we come to the contribution of astronomy to the SDG 8, the economical growth and decent works, how through the activities that we are doing in Ethiopia and under the department, we can contribute to this. So the first is the development of the institute. When we started in 2016, we really started from scratch with all the institutional developments, establishing of the departments and so on. And now we have currently more than 170 staff members, but the majority of them are young people with BSc degrees, some of them with MSc degrees. So a lot of work has been done over the past few years on the human capacity development, not only in the field of astronomy, but many other supportive fields like computer science, computer sciences, engineering, which means that we really can improve the skills in a longer term. Research is also an important point. And the science development, and we have currently 4 research groups that are running, and I will just briefly show here the different projects. I will not go into the details of any of them, but different projects that we are running under the extragalactic group on the study of the nuclear activity in galaxies between Ethiopia, Rwanda, Uganda, Tanzania, and South Africa. And you can see here some of our very first master and PhD students in these countries that I just mentioned. When we come to the infrastructure development of astronomy in Africa, I think it's one of the really significant contributions to the SDG 9. In Ethiopia, we currently have the small observatory with 2 small telescopes. We had so many challenges to put these 2 observatories operational, and the site testing is now going on at the north. Ethiopia has a dream to really become one of the future astronomical sites. And here it's just a brief summary on the infrastructure that is going on across the continent in radio astronomy especially, but in optical as well, through the site testing and the small observatories and then SALT that we have in South Africa as well. Now, through the previous SDG, just a brief mention is that also we can directly and indirectly contribute to the SDG 13, the climate action and the sustainable energies. For the first one is through the protection of the astronomical sites and all the site testing, where we have South Africa as an example. And then in the second case, through the SKA development and all the novel and the study of the new renewable energy sources that is currently going on for supporting SKA, but that will be having the application in the whole society. When we come to the SDG 17, again, astronomy is a great example and a very powerful tool for promoting long-term collaborations. We have SKA Africa as one of the biggest international collaborations in terms of the science. You can see here the list of the institutions that Ethiopia, under the Department of Astronomy, we managed through research to establish the collaborations. These collaborations have been also strengthened through different meetings, conferences that we organized. Some of them are listed here. And I would like to mention the IAU symposium that we organized in 2019, that has been only the third IAU symposium to be organized in Africa over the last 100 years of the IAU, and then the first one for the East African region. And other activities are also there. Other examples through the African Astronomical Society. We are now trying to strengthen the collaborations across the continent through the Astronomy in Africa survey and the science portal that we are developing. And then we are really looking forward to the IAU General Assembly, the first one to be organized in Africa in 2024. And under the Science Committee of the IAU General Assembly 2024, we are now looking to the possibilities how we can use this event to really strengthen the collaborations between Africa and the rest of the world as well. And this is, I'm finalizing, this is one of the last SDGs that I will mention, how through astronomy we can also contribute to make our institutions strong. It's related with what I said previously, but also the important point is the policy development that is now going on across the continent in different countries. So in Ethiopia as well, we now, over the last 4 or 5 years, we worked first on the very first Ethiopian space policy and strategy, and now we are working on the national 30 years roadmap. And this is really important for putting the long-term engagement of the decision makers. And we are also having now the African strategy for fundamental and applied physics that started a few months ago. And under this strategy, we have also the working group for astrophysics and cosmology. And we believe that this strategy, again, on the continental level, will benefit a lot, not only in terms of astronomy, but physics in general. So to finalize, when we combine all of the previous that I mentioned, we can definitely contribute in the long term then to these two SDGs that are really fundamental, that we reduce inequalities across the world, and that we also fight the poverty in the long term. So I will finish my talk with these two messages. And I would like to mention that as you could see, there is really a lot going on, but most of the African countries are still in a very initial phase through the institutional development, human capacity building, and still the number of qualified people is small in comparison with all the people to be trained. So definitely all the support is very important and welcome. So thank you very much. As I said, I will stop with these two messages. And I would like to give a stress to this image here that was a slogan of the Great Ethiopian Run that is organized every year with thousands, tens of thousands actually of people running. And in 2018, you could see all of these people running with this slogan on their back. So thank you very much.
Thank you, Mirjana. Congratulations on your work and the work you're doing for Africa, but also for astronomy. So you have quite a few questions. There's going to be time for just one. All the others are going to pass over to Slack, and Mirjana will answer them later. So the question comes from Christine Ackerl. Thanks for showing your impressive work, Mirjana. Congratulations. I'm wondering how you tackle language barriers in your work, especially when working with children.
Yes, language barrier is a huge barrier across the continent because in every country we have a big diversity. So it is really a problem. In Ethiopia, we have more than 100 languages. And the official language when you come to the higher education is English. So that there is no any discrimination between different ethnic groups. But even when we come to the master PhD courses, we can see that students are struggling with English because they have to do a double job, you know. So definitely language barrier is there. And I think it's one of the important points to be raised in future regarding the science development under the African Astronomical Society. Now we have more and more conversations regarding that. When we come to the activities on the local level in Ethiopia, well, it's always between English and local languages as well. We always manage to have people who can speak some of the local languages where we do activities, so that the interpretation can be translated. And we are now starting different development of different, for example, now we are developing one book regarding the role of astronomy, space science for the society, and we are planning to do it in several languages in Ethiopia. So yes, so it's a good question. It's a big issue everywhere, but when you come to the African continent, it's really a big challenge. Yeah.
Thank you for your answer and for your wonderful talk. And then we will move to our next speaker.
Thank you, everybody.
Our next speaker is Philip Diamond, SKAO General Director and Professor, University of Manchester, who will tell us about the SKAO report. So Philip, the floor is yours. I'm going to give you a 5-minute warning, if that's okay.
Thank you, Sara. Can you see my front slide?
Perfectly.
Thank you. And good afternoon to all. It's a pleasure to be speaking to you today. I'm here to give you an update on the status of the square kilometer array. But actually, this is going to be a very special update. So I hope you stay with me for the next few minutes. I will start with this introductory slide because not everybody, I understand, will be fully familiar with the square kilometer array. So the SKAO, the SKA Observatory, is a global collaboration of 16 countries. And the mission of that collaboration is to build and operate the next generation radio astronomy facility. The observatory itself is a brand new intergovernmental organization, second only in astronomy after ESO. So we are an IGO governed by a treaty, and the SKAO was actually born in February of this year. It's headquartered at Jodrell Bank near Manchester in the United Kingdom. And the 2 radio telescopes will be the 2 largest radio telescopes ever built. And they will form the observational element of the SKAO. So the 2 artist impression that you see on the screen now represent what we will be building. So SKA low, the low frequency array spread across 65 kilometers of Western Australia is shown in the bottom left corner. And in the bottom right, you see a representation of SKA mid, the mid frequency array of SKA, which will have 197 15-meter class dishes. 64 of them, of course, already exist as Meerkat, and we will be incorporating Meerkat into SKA mid. This whole network will generate an enormous amount of data, up to 700 petabytes per year of scientific data, which will be made available to the scientific community through a network of SKA regional centers, which will act as a portal to the data. It will take 7 to 8 years to build SKA, and our cost estimates is 2 billion euros for the first 10 years. That includes the construction cost and the operational cost for that period of time. And of course, our ambition is much greater, as you see across the bottom of the screen. But for now, I will only focus on SKA phase 1. This map of the globe shows you the countries that are participating in SKA. We have 7 formal members of the observatory. They have ratified the treaty. You see the asterisks under their flags across the below the map there. And we have 9 other countries that are observers to the Council. And these countries are in various stages of within their governments pushing through the process to join the observatory as members by ratifying the treaty. Of course, we're building the SKA to do science. I have no time to talk about the enormous range of science that will be enabled by the SKA, just that it is a huge range, covering almost the entire history of the universe, from cosmic dawn to local phenomena in our own solar system. So that's summarized on that slide that you see now. I'm now going to take you on a short history of the SKA, and you will see why in a few minutes. So it has been a 30-year journey from the early concepts. Those early concepts were captured and summarized in a paper entitled The Hydrogen Array, given by Peter Wilkinson, the University of Manchester, at a conference in 1991, celebrating 10 years, it was actually 1990, celebrating 10 years since the VLA had started observations. And I do note that in August of this year, our colleagues in the US are celebrating 40 years of the VLA. And in that 30 years, the ideas behind the SKA, they grew from those early concepts to the design that we have now. We've had 20 years of technology exploration, from ideas such as the Lüneburg lenses, which were never as effective as hoped, through the Canadian concept of large aperture reflectors with fairly flat screens of reflecting metal on the ground and balloons holding up receivers. They even built a prototype balloon, as you see there. There was the Indian concept of preloaded parabolic dishes, 12 meters in diameter, with LOFAR type low frequency antennas on the circumference. That idea never came to fruition. There was the US concept of many thousand small dishes. This was prototyped in the Allen telescope array. Our Chinese colleagues had proposed a large number, a significant number of large single dishes, such as was eventually built for FAST, which you see in the picture on the screen now. And then there are concepts still in development, which are future concepts, such as the mid-frequency aperture array. It's also been 12 years since the first tentative steps towards an intergovernmental organization. And this started with European Commission funding through the Framework 7 program of PREPSCA, the preparatory study for the SKA, which among many other things had a work package on governance. And that, with external legal advice, explored 5 different options: treaties, foundations, companies, etc., agreements, MOUs, etc., the possible range. In fact, the SKA organization itself, which was founded in 2011, was indeed emerged from this. It was a company. At the time, we were leaning towards, in the long term, a treaty because of the autonomy it brings, the flexibility for procurement, etc., etc. We were warned that the downside is that the process to require ratification meant that the process is lengthy, and it did indeed turn out to be lengthy. It's been 10 years since the SKA organization, the not-for-profit company, was established. And here I just extract the three objectives: carry out the business plan, select a preferred site for the SKA, and develop an organizational framework for the construction and operation of the SKA. So the year after the organization was formed, the site decision was taken, which in the end was the dual site decision to locate the low frequency array in Australia and the mid frequency array in South Africa. And I think looking back, this was absolutely the right decision to have taken. It's 8 years since the detailed design process began with the formation of the design consortia, who have done a superb job in working with the SKA organization, as was then SKAO now, in developing the design of the telescopes. It's been 6 years since the IGO negotiations began in Rome, and the science book was published. This is a picture of one of those early IGO negotiations. And those of you who have sharp eyes will see me and my SKA organization colleagues sitting at the back of the room. We were not around the table. We were advisors in this process. It was the members who were negotiating the text of the convention. In that same year, we published the superb 2-volume Advancing Astrophysics with a Square Kilometer Array, a good 9.8 kilograms of scientific goals for the SKA. We also had several years of system preliminary design reviews, element critical design reviews, signing of the convention, first ratification, actually by our Dutch colleagues, and the overall system critical design review. We have had a large number of external design reviews, and I do thank all of those who've been very professional in the process of giving their time freely to these design reviews and helping us refine the telescope itself.
5 minutes, Philip.
Sure. The convention itself was signed, as many of you will be aware, at a ceremony in Rome, March 2019. These are the 7 founding members these are representatives of the 7 founding member countries of the SKAO. And since that time, we've had all 7 have now ratified the convention. As I've mentioned, others are in the process of joining. You may have seen the announcement by President Macron that France intends to join the SKAO. Other countries are in a similar situation. We entered into force in January, and on the 4th of February this year, the SKA was born. 1st of May this year, we transitioned all of the staff from the not-for-profit company, the SKA organization, to the observatory. And then on Friday, it was my privilege to put this recommendation to the SKA Council. And I did so on behalf of all who work or have worked for the observatory and all those many thousands of people around the world who contributed to the design and the scientific definition of the SKA. I won't read the whole thing. I will just say that I recommended that the SKA Observatory Council approve the commencement of the construction of the first phase of the SKA. And I'm very pleased to say that in that meeting on Friday, they approved that the start of construction can happen. And what we call T0, which is the formal start of that process, is in 2 days' time, the 1st of July. We won't see shovels in the ground on the 1st of July. What we will see is invitations to tender for much of the infrastructure work being issued. From that date, we have a total of 75 contracts which will have to be issued for construction of both telescopes. These are 75 major contracts. So that will be proceeding from the 1st of July. And our intent, and we have kept to schedule pretty much over the last 15 to 18 months, our intent is that SKA construction will be completed in 2028 or 29. We have some schedule contingency in there. So that's all I need to say as part of the update for the SKA, and thank you very much.
Thank you very much, Philip. Any questions coming? Let's remind the audience that you can ask questions through the Q&A chat. Sorry, I have a rather loud fan. So it doesn't look like there's any questions so far, unless Mark is not pushing them. But Mark, any questions? Do you see any questions on the Slack? No, doesn't look like we have any questions. Well,
Sara,
Sorry, I was muted.
sorry, yes, go ahead.
Yeah, could I just say one thing? I would like to congratulate Catherine Cesarsky, who is the chair of the SKAO Council, who is receiving the Jonathan Tate Medal in the next item on the agenda. I could not think of a person more deserving of such a medal. So congratulations to her.
Definitely. Yeah, definitely. You're getting thanks about the talk that was very informative by Michelle Boyce. But I don't see any other questions. So I'll remind the audience you have a few more seconds to ask questions. And if you have questions later, you can ask questions in the Slack, and Philip will join the Slack space to answer question there in the plenary channel, hopefully. Okay. So our next item, like Philip already mentioned, is the presentation of the American Institute of Physics Tate Medal. Introducing the event is our president, Roger Davies.
Thank you very much, Sara. So Phil's presentation reminds us how international astronomy is, and it's wonderful to see Mirjana's talk showing us how observational astronomy is vital in Africa. It is, of course, in Africa that Eratosthenes made the first measurement of the size of the Earth. Remarkably accurate it was too. That brings us very neatly to the idea of international leadership in astronomy. And it's my great pleasure to introduce two figures from the American Institute of Physics, David Helfand, the chair of the board of directors, and Mike Maloney, the CEO of the American Institute of Physics, to award the Tate Prize for International Leadership to Catherine Cesarsky. Over to David and Mike.
Thank you very much, Roger and Mark and everyone else who made it possible for us to present this award at your meeting today. I first met Catherine 42 years ago this week at a NATO Advanced Study Institute in Eritrea, organized to discuss the exciting results from the first imaging X-ray telescope, the Einstein Observatory. She was working on the origin of cosmic rays and their interactions with molecular clouds, which was a subject of considerable interest to those of us who were using this telescope to obtain the first X-ray images from supernova remnants interacting with such clouds. Well, hundreds of papers later, Catherine has published on observational and theoretical problems ranging from stars to the cosmic microwave background, and from 10 to the 19th EV cosmic rays to 10 to the -6 EV radio observations of deep survey fields. Her first project as an undergraduate, however, involved building a radio telescope, something I didn't know. And while her graduate work was in theoretical high-energy astrophysics, the satisfaction of building new instruments must have been deeply instilled, because she went on to become the principal investigator on ISOCAM, the main camera on the Infrared Space Observatory, and then as Director General of ESO, oversaw the inauguration of the VLT. Then, in what must be, in my view, the single most technically and politically complex astronomical project ever undertaken, she launched the construction of the Atacama Large Millimeter Submillimeter Array at 5,000 meters in northern Chile, a project that is revolutionizing our view of planet and star and galaxy formation, and has brought us the first image ever of a black hole. She also commissioned the study that is leading to the ELT, a 39-meter diameter telescope now under construction. It will increase by more than an order of magnitude the sensitivity of the world's largest telescopes. She's also chair of the board, as you just heard, of the Square Kilometer Array, yet another international consortium of 16 countries, this time involved in planning for the construction of yet another world-leading telescope that will increase our ability to scan the universe at radio wavelength with orders of magnitude more sensitivity than at present. As president of the International Astronomical Union, Catherine launched the International Year of Astronomy in 2009 to celebrate the 400th anniversary of Galileo's first telescopic observations of the universe. It is easy to imagine that in another 400 years, in no small part because of her leadership, this time will be remembered as an equally important historical epoch when we opened new windows on the universe and came to understand quantitatively our place in it. Catherine is High Commissioner for Atomic Energy in France and a member of the Consultative Committee of the European Atomic Energy Community for Fusion. She is a Grand Officer of the Legion of Honor and a member of the French, Swedish, and US National Academies, as well as the Royal Society. The John Torrence Tate Medal of the American Institute of Physics was first awarded 50 years ago this year and recognizes international leadership, statesmanship, and service to the physics community. I'll now turn the floor over to Dr. Michael Maloney, CEO of the AIP, as he welcomes Dr. Cesarsky to join Abdus Salam, Eduardo Amaldi, Raoul Sagdeev, Neil Turek, Fabiola Gianotti, among others, as their 16th Tate Medal awardee.
Thank you, David, and thank you to our colleagues at the EAS for hosting us today. Good morning, good afternoon, good evening, so depending on where you are in the world. I'm here in California this morning where we're just getting started with Tuesday, and it's a great pleasure to make this award to Catherine, who I first met when we served on the Bureau of COSPAR ICSU's Committee on Space Research for some delightful meetings in Paris some years ago. So it's an honor to be surrounded by friends on such a great occasion. And as David mentioned, we are honored to award Catherine the John Torrence Tate Medal for 2020. The medal, as David mentioned, was established in 1959 and recognizes leadership and service to the physics community on an international level by a non-US physicist. Services that further international understanding and exchange are considered to be of primary importance in the making of this award. The citation from the committee that was chaired by Charlie Kennel and included Sir Stephen Cowley, Professor Margaret Leinen, Professor Wu Ji, and Lord Martin Rees, an international committee of quite distinguished experts, read, "For her leadership in bringing to fruition some of the most important international astronomical observatories, for her statesmanship through her approaches to the highest political leaders in France, Europe, and Chile, and for her service as president of the International Astronomical Union, among other prestigious organizations." The award consists of a bronze medal and a certificate, which I know Catherine has, and a cash award of $10,000. And we're delighted to be able to make the award today. And Catherine, it's a great pleasure to meet you virtually. I regret we're not able to hand over the medal in person, but hopefully sometime in the near future, we'll be able to meet and celebrate together. So thank you so much, Catherine, and congratulations.
Thank you very much, David and Michael. And indeed, it would have been so much nicer to meet in reality. And there was a dinner expected. So indeed, you still owe it to me. So I really want to thank the American Institute of Physics for giving me this award. Receiving the Tate Medal was a complete surprise and really a very nice one. And since you don't have it, I'll show you the medal and the plaque. I don't know how much of it you can see. Because I put a background, you can't see it, but it's a huge bronze plaque, something that I will always remember. So after my university studies in Argentina, I had the luck of being a graduate student at Harvard and a postdoc at Caltech. The rest of my career took place in Europe, mostly in France, and I am very integrated in the European science community. But I always felt, as many astrophysicists do, that I am in fact a citizen of the world. All my life, I have kept strong contacts with US colleagues and institutions and went back there for visits and sabbaticals. And of course, we Europeans and Americans built together with East Asia the ALMA array in Atacama, as you mentioned. So I am always happy when I see that I am remembered in the US, a hospitable country to which I owe so much. Thank you.
And thank you, Roger, for that. And thank you. We'll hand it back to you.
Thank you very much. And let me add my congratulations to Catherine. What a tremendous award and a tremendous and recognition of a tremendous series of achievements. We owe you so much, Catherine, and we wish very much to be able to celebrate with you in person one day.
Yes.
And thank you very much to David and Mike. We'll move on with the rest of the program now, so I will hand over back to Sara. Thank you.
Thank you, Roger. Let me join you in congratulating Catherine on her many achievements. And we will now go back to some of the last two scientific presentation of the program of the plenary session today. So our next speaker is Anders Johansen, Professor of Astronomy at Lund Observatory in the Department of Astronomy and Theoretical Physics at Lund University in Sweden, and also Professor of Planetary Sciences and Planet Formation at the Globe Institute at the University of Copenhagen. The title of the talk is The Roles of Pebbles and Migration in Planet Formation.
Okay, thank you very much for this introduction. I hope you can all hear me and see me now. It's a really great pleasure to be here and talk to you today, although of course I wish I could have done this live. Let me share my screen and get right to it. If I can find the right one, I have it here. And then I will also select the full screen, enter full screen. And now you should be seeing the full screen. Right, so the title of my lecture today is The Roles of Pebbles and Migration in Planet Formation. All right. So today we can actually photograph how young planets form in protoplanetary disks around young stars. These are 8 examples of protoplanetary disks photographed with the ALMA telescopes in Chile within the last few years. So planets form in such protoplanetary disks, and they consist of gas and dust. What we're seeing here is actually the thermal emission from cold pebbles of millimeter sizes, and the scale here is approximately 50 to 100 to 200 astronomical units, the astronomical unit being the Earth-Sun distance. So what we're seeing here are protoplanetary disks about the same scale as our own solar system. The reason we are seeing the dust and not the gas is that the gas is transparent. These disks are cold. They are maybe only 50 to a few hundred Kelvin in temperature. So the 99% gas, mainly hydrogen, is mainly transparent, while the 1% dust and ice particles carry a significant opacity at these millimeter wavelengths, which we are observing at here. So as I said, typical sizes of 100 astronomical units, and the typical disk mass is actually quite massive, between 1% and 10% of the mass of the central star, at least early on. So planet formation is a race against time because these disks only live for a few million years. And in that time, we need the dust and the gas to come together to form planets. This plot here shows a distribution function, a measurement presented by Tukunyk et al. 2018, also with data from other papers, where we can see that when we go along the classes of young stars from class 0, class 1 up to class 2, we go through an evolution of a few million years in the evolution of the star and of the protoplanetary disk. We see here the logarithm of the dust mass in Earth masses, so 1 Earth mass, 10, 100, 1,000 Earth masses here. And we can see here that the class 0 and 1 disks that are very young actually contain from 100 up to a few hundred Earth masses on the average, and some of them contain even more. But then as we go to the class 2 phase, which is probably setting in after 1, 2, 3 million years, we see that the dust mass falls drastically, and we go down to just a few 10 Earth masses after a few million years. So protoplanetary disks live apparently only for a few million years, maybe 2 or 3 million years. And the reason that they don't live very long is that the gas and the dust and the protoplanetary disk is both accreted onto the star. Some of it is photoevaporated, and some of it is also incorporated into planets. But this gives us this race against time that dust must grow rapidly before the disk is emptied onto the star. Now, in the first step of planet formation, the micrometer-sized dust that we start off with the ISM sticks together and grows up to approximately millimeter sizes. Many people have worked on this coagulation problem where micrometer-sized dust particles stick to form larger sizes. I'm presenting here a global simulation that I did, that my PhD student, Lene Eriksson, presented in 2020, just to show you what it looks like when you start with micrometer-sized dust. Just look at the top plot here, micrometer-sized dust in the protoplanetary disk that goes out to several hundred AU in size. We see after 50,000 years, we are blue, green is 200,000 years, and cyan here is 350,000 years. We see we grow very, very quickly up to a millimeter in size in the inner disk. And then in the outer disk, the growth takes longer. So you see the blue here, and then the green, and then the cyan. But we see eventually we get up to this 100 microns to 1 millimeter in size, simply by sticking and in the collisions. So why doesn't the dust grow any further? That's because when they come to these millimeter sizes, the dust aggregates, they fragment when they collide, or they bounce when they collide, and they can't grow to larger sizes then. There's an additional problem here, and that comes from the migration, that the pebbles are actually drifting towards the star due to friction with the gas. So that's an additional reason why they're not growing so fast. So this is fine for forming pebbles, but we want to form planets. And the first step in forming planets are kilometer-sized planetesimals. And we clearly don't form them here. So we need some kind of help from gravity now to form planetesimals. But we can't invoke the gravity between two pebbles. They have a too low gravity between them. We need to have a lot of pebbles coming together in a small area in order for the collective gravity to bring them together to form planetesimals. So we need some way to concentrate the pebbles in the gas. And that's something that we in the planet formation community have been very focused on in the last 1 or 2 decades, I would say. Now, one mechanism by which pebbles can become concentrated in the gas is by the so-called streaming instability. There are other mechanisms also, but I will focus today on the streaming instability because it's a very efficient and very well-explored mechanism. So this is sort of a slide that illustrates the essence of planetesimal formation by the streaming instability. We start with these micrometer-sized dust grains that are part of the ISM and go into the protoplanetary disk. They then collide and stick together to form pebbles between millimeter and centimeter sizes. But these are not pebbles, igneous pebbles like you would find on the beach. These are dust aggregate pebbles, and they are very, very fragile. So when they collide with each other, they don't stick very well with each other. But then as these pebbles are drifting towards the star, they actually undergo spontaneous concentration by the so-called streaming instability. And let me explain to you here how the streaming instability operates. So this square here represents a small stamp in a protoplanetary disk around the star. And you should imagine that the star is here somewhere to the left. The arrows that are pointing down here represent the gas motion relative to the Keplerian speed. You see that it's negative. We are co-rotating here with the Keplerian speed. The arrows pointing down show that the gas is actually orbiting slower than the Keplerian speed. The reason that the gas is orbiting slower is that it feels not only the gravity from the star. So this is the star. Then here's some gas orbiting around. So the gas doesn't just feel the gravity from the star that would make it orbit with the Keplerian speed. It also feels a slight pressure gradient pushing it out. There's a higher pressure and a higher density close to the star, and a lower pressure further away from the star. And that acts like a little bit of a compensation of the gravity. That means that the gas will orbit a little bit slower than the Keplerian speed. Now this operates as a headwind onto the pebbles. So here's a millimeter-sized pebble. The pebble will get headwind. It will lose angular momentum, and it will spiral into the star. Now, the essence of the streaming instability is that if we can start to concentrate some pebbles in a filament a certain distance from the star, then those pebbles can locally act as a drag force onto the gas. So they can drag onto the gas. They can force the gas to orbit closer to the Keplerian speed. That means that the headwind here becomes slower. As I'm showing with a shorter arrow, the gas is orbiting closer to the Keplerian speed. That means that the radial drift speed becomes lower since there's less headwind. And now we have a runaway effect whereby more and more particles are coming into this filament. The filament gets denser and denser. It increases its ability to accelerate the gas towards the Keplerian speed. And this way we get a runaway process that we call the streaming instability that can concentrate a lot of particles in a dense filament. We see here what it looks like in an actual computer simulation where we have a 3D simulation. We see it in the 2D here. And we include the gravity between the pebbles. We see the filament that has formed here by the streaming instability. Then it's become very, very narrow by the gravity between the pebbles. And as the filament contracts, it becomes so dense that it undergoes a collapse to form planetesimals with a wide range of sizes. These are all of the little dots which we're seeing here. So filaments collapse by gravity to form planetesimals with sizes from 10 kilometers several hundred kilometers. And most mass actually ends up in 100-kilometer sized planetesimals. That's sort of a typical asteroid in the asteroid belt. This is a picture of Lutetia in the asteroid belt. We also form some smaller objects down to 10 kilometers. That's maybe more like a comet, like 67P as we're showing here. And then something very exciting. Occasionally, when we run at very, very high resolution, we actually form binary planetesimals. So just like binary stars, we have two planetesimals that are orbiting around each other. We don't have many of these in the asteroid belt, but actually there are many of them in the Kuiper belt beyond Neptune. There are many, many binary planetesimals there. And I will return to this important point in the next few slides. I want to make a point here that in order to trigger this streaming stability at all, we need the pebble metallicity, so the dust to gas ratio in pebbles, to be increased a little bit above the solar value, either by piling up dust or by gas filter evaporation. And that was the work on studying the conditions for the streaming instability was what won Joanna Draskowska the Career Award of the Astronomy and Astrophysics Journal that was presented to her yesterday. Right. Okay. Now I want to return a little bit to the Kuiper belt, where I said that there are many binary planetesimals in the Kuiper belt. So this object here is called Arrow-Koth. It was visited by NASA's New Horizons mission in 2019 when it flew past it. Many had expected that it might have been a binary, but it turned out to be something even more interesting. It's a contact binary. So it's two components of a planetesimal lying perfectly on top of each other. So the New Horizons team published 3 papers in Science in February 2020. And analyzing this, they concluded that these two components, they must have been a binary originally, and that these two components then collapsed at a speed of less than 3 meters per second. That's really like a walking speed when it comes to what we normally think about in astrophysics as the relevant speeds. So we see here when we collide the two components in a computer simulation at 10 meters per second, both components get destroyed. At 5 meters per second, there's significant damage to the neck, but at 3 meters per second, these two components can gently land on top of each other, completely undamaged. So the New Horizons team concluded that this is a support for the gentle accumulation model, which streaming instability is a part of, in contrast to the violent collisions model or hierarchical growth model, where planetesimals would grow by collisions between planetesimals coming from different directions. But those collisions would then happen at kilometers per second, and that could never lead to an object that looks this way. Pluto's and Charon's impact on mass function is another interesting aspect of the NASA's New Horizons missions, because they could look at the craters on Pluto and Pluto's moon Charon, and they can actually see that there's a lack of small craters there. There's a lack of small planetesimals then in the Kuiper belt, and this also sort of fits the initial mass function of what we have from the streaming instability simulations, that there are missing planetesimals below a few kilometers in size. All right. To stay with the binaries, we can also go down to Earth again, and then we can study binaries in the Kuiper belt. And it actually turns out that many of those binaries orbit around each other in the same way as they orbit around the sun. This is called prograde rotation, just like the Earth spins prograde around its axis. So this is a study from Untitled 2019 that shows a lot of binaries in the Kuiper belt. And then we see here the separation of the binaries in units of neutral Hill radii. And we see here the obliquity of the orbit around each other, where 0 to 90 degrees is prograde, that's like Earth spinning around the sun, and 90 to 180 degrees is retrograde, so that's basically going the other way. Yeah. Now there's a clear preference for prograde rotation here. We see it here in the cumulative distribution. Here's the binary inclination, here's the cumulative number. The dashed line here is the observational data, and we see that approximately 80% of the Kuiper belt binaries, they spin in the prograde direction. Now, Nesvorny et al. In 2019, they took a simulation of the streaming instability at very high resolution, and they studied all those clumps that form, and they found that they generally rotate prograde also. When they took these clumps out in a separate simulation, let it collapse to form a binary, those binaries tend to spin prograde also. We're seeing from the simulations the black line here, which is in a very good correspondence to the dashed lines here. So that made the cover of Nature Astronomy with the title Fingerprints of the Streaming Instability. We saw something similar in our paper in 2015, that the binaries show a strong preference for prograde rotation. And the interpretation of Arrow-Koth with the two perfect components lying on top of each other is then that it was a collapsed binary that formed by the streaming instability, and maybe it collapsed because of gas drag, because it formed within the protoplanetary disk. Okay, so that was a little bit about planetesimal formation, but we have to move on and also form full planets. And unfortunately, the race against time is not over yet because planets tend to migrate. So planets migrate towards the star because of the gravitational torque from the protoplanetary disk. So if planets don't grow fast enough, we will lose all the planets into the star. So planets have to grow really fast. Unfortunately, they don't in the classical picture of how a planet forms. And in the classical picture, a protoplanet is growing here to become a planet by creating this person here, which is a planetesimal that could be several hundred kilometers in size. Now the circle here, the dashed line represents the gravitational scattering radius of this planet, of this growing protoplanet. And we see when the planetesimals come within, it comes within the gravitational scattering radius, then it gets, well, gravitationally scattered, and it moves away on a more eccentric orbit, and that makes it harder to accrete the planetesimal next time it comes around. Now, on the other hand, if we replace the planetesimal with a pebble, a millimeter to centimeter size pebble, that's the little dot here, then on the way to getting scattered by the protoplanet, it loses so much kinetic energy to gas drag that it goes from being gravitationally unbound as it's far away from the protoplanet. And as it then moves towards the protoplanet and loses energy, suddenly it has a totally negative energy, which is gravitationally bound, and it has no choice but to spiral and collide with the protoplanet. So pebbles are accreted much faster than planetesimals due to energy dissipation by gas friction. And then we can actually show that planetary growth by pebble accretion can outperform migration. So even if planets migrate, pebbles can actually grow. Planets can grow faster by pebble accretion than the migration. I show an example here of what we call growth tracks of planets forming by pebble accretion. Here's the distance from the star in astronomical units. Here's the mass of the planet in Earth masses. And we can start out in the 2030 AU region first. That's where CO starts to freeze to become ice. And we can see when we start early on, we can form a core of 10 Earth masses here. That's the blue line. We can start to accrete gas. We can migrate massively, and then we can yet avoid running all the way into the star because we have grown so fast here that we can actually end up in regions that are sort of in Jupiter-Saturn mass region, 100 to 300 Earth masses, and also in the Jupiter-Saturn distance region. And we can do that because pebble accretion is so fast. If we start instead of the water ice line, very interestingly, then if we start early, we can form something like a hot Jupiter here. A core grows fast here at 3 AU, accretes gas and migrates in towards the star. And as the water ice line moves closer to the star with time, as the stellar luminosity is dropping with time, then the core masses get so low that they only accrete a little bit of hydrogen and helium here. They become more something like a super Earth. But can we find any evidence that pebble accretion actually happened? Can we find any evidence that migration happened? If migration happened, for example, in the solar system, then we would probably conclude also that pebble accretion must have been the way that Jupiter, for example, outcompeted the migration. Jupiter's at 5 AU today, and we can actually find evidence of Jupiter's migration in its Trojan populations of asteroids. So here's Jupiter, here's the main asteroid belt, here's Mars, and in front and behind Jupiter, there are 2 populations of Trojan asteroids that are orbiting in stable orbits. It's really mysterious, though, that there's 1.6 times more Trojans ahead of Jupiter than there is behind Jupiter, and this is completely unexplained in the standard planet formation picture. Now you can see this asymmetry ratio here, and then you can see a model here where we form Jupiter in situ at 5 AU. So as you say, these are models led by my PhD student, our postdoc, Simona Pirani, where we form Jupiter in situ at 5 AU. We have no asymmetry between the leading and the trailing Trojans. We have an asymmetry ratio of 1. They're equally many trapped in each. Then we try instead to have a migration scenario where Jupiter forms further out, at the most extreme beyond 30 AU, at the least extreme beyond 7 AU. And then we let Jupiter in in-body simulation, we see Jupiter here, Saturn, Uranus, Neptune. We let Jupiter migrate through the disk and through a population of planetesimals of different colors here. And we can see as Jupiter and Saturn migrate through the disk, the planetesimals are scattered all over the place. Some of them into the asteroid belt, some into the Kuiper belt, some to the Oort cloud, and some are trapped as Trojans of Jupiter. And when we then look at the asymmetry ratio, we see an asymmetry ratio is almost exactly what we're measuring from observation, about between 1.2 and 1.6 or something like that. We see the asymmetry ratio only gets important when Jupiter migrates at least a handful of astronomical units, so a significant migration. Another piece of evidence here is that Jupiter's Trojans have the same color as Neptune's Trojans, and Neptune is sitting out of 30 AU today. And we believe that's an evidence that we should probably prefer some of the tracks out here where Jupiter migrates from significant distances and form in close distance to Neptune also. So the Trojan asymmetry may thus be the first really concrete evidence we have that Jupiter's core grooves most of its mass far from the sun, and that Jupiter experienced significant migration while it was forming. So if there are so many pebbles in protoplanetary disk and they drift through the protoplanetary disk, they most certainly affect the inner regions of the disk also, where terrestrial planets form, and also super Earth. But that was a question asked by Michael Lambrecht in a collaboration with me and many other people in 2019. What happened to the inner regions of the protoplanetary disk? So we can take an n-body simulation now. We can take a number of planetary embryos, start them at the moon mass, 10 to minus 2 Earth masses, and then let them grow by creating pebbles, let them migrate, and let them be able to collide with each other. So the pebbles are drifting through the disk at a rate of approximately 100 Earth masses per megayear. That's a lot of building material going through the inner solar system also. When we take sort of a nominal pebble flux, a bit of a low pebble flux here, we see that the embryos, they grow and they migrate, and they end up with a mass maybe around a few Mars masses. So Mars is 0.1 Earth masses. After 3 million years, we have a perfect lineup here of Mars mass protoplanet. And when we run that for 100 million years in n-body simulation, we can see we end up with something like Earth, Venus masses here, and something like Mars masses here. This is actually a good picture of classical terrestrial planet formation. That's how we normally think terrestrial planets form. However, if we increase the pebble flux a little bit here to a little bit higher values, just a matter of 5/3 times the nominal flux, then something dramatic happens. There's a whole almost phase transition here, where the planets grow faster, they migrate more as they grow, they start to collide with each other. We see growth tracks that end here as these things collide. And we end up with a collection of bodies between 1 and 10 Earth masses now. This is what it looks like at the disk dissipation at a high flux and a very high flux. And when we run for 100 million years, we get beautiful systems of super Earth out. Yeah? So a high pebble flux leads to the formation of super Earth systems. And this way we've shown here that the formation of super Earth and terrestrial planets may be connected processes. A high pebble flux gives super Earth, and a lower pebble flux gives terrestrial planets. I want to make a point here. That is, when we run these simulations, particularly at this stage here, a lot of these planets are sitting in resonant chains. So all the planets are orbiting in orbits that are integers of each other. That has to do with the migration and with resonant trapping. And there's a lot of trapping in resonant chains. If you just follow the distribution function here for the dashed line here, we see at the end of these simulations here, a lot of the planets are trapped in 5 to 4, 4 to 3 resonances. That's not at all what we observe. We started with the Kepler satellite, where we observe more something like this green line here, that there's not much preference for resonances. But running it for 100 million years, there's so much instability between these planets that the resonant chains, they break up, and and that leads to a reduction in the planet number and an increase in the separation. And then you can see that we can get this line here, which is this distribution here, to match what is observed with the Kepler satellite quite well. Okay. Now I want to just end with one slide here, where I do something that's maybe a little bit heretic here, which is to suggest that our Earth formed by pebble accretion also. So this paper from 2021, I wanted to explore a little bit what happens between these two cases. Can you also form Earth and Venus by pebble accretion? It turns out that it works actually quite well. If we start planetesimals at 1.6 AU, everything there, and let them grow by pebble accretion and let them migrate, we can see we get a good match to Venus here at 0.8 AU and 0.8 Earth masses. We get a good match to Mars here. We don't get such a good match to Earth here. We get something that's 0.6 Earth masses and not 1 Earth mass. But then we create an additional planet out here that's called Theia of 0.4 Earth masses. And then later on, Theia will collide with Earth to form the moon. And then Earth will jump from this point up to this point here. Yeah. We think this is a good model because this way Theia and Earth get the same composition, and this can explain why the Earth and the Moon have the same composition. And also, it's not. We think that it's not completely random that Mars has the mass it has on Earth and Venus has the masses that they have. So this is an indication that there was a planetesimal build at 1.6 AU that underwent pebble accretion, and that this is the reason why the planets in the solar system, in the inner solar system, have the characteristic masses and orbits which they have today. We can also, instead of kind of searching for the best solution here, we can Monte Carlo a little bit around this, and we can say from the black lines here, what if we start planetesimals a bit randomly between 1.6 and 1.7 AU and a little bit random in time. And then you can see you get this black population of planets here that are sort of matching Venus, Earth, and Mars pretty well. If you make the planetesimal belt wider, as with the green dots here, we get a little bit more solutions all over the place and not such a good match to these planets. And if we increase the metallicity a little bit, have a little bit more pebbles, increase to sort of the solar metallicity from a little bit below the solar metallicity, we can see that most of the planets now grow up to super Earth and they overshoot the sort of Venus, Earth, Mars regime here. So this sort of means that we go more towards this regime here from the Lambrecht et al. Paper. All right, I've come to my summary of this lecture. I want to say that many particle concentration mechanisms are known. I focused here mainly on the streaming instability because it's very powerful in driving high pebble concentration and driving gravitational collapse to form planetesimals. The characteristic size of planetesimals formed by the streaming instability is about 100 kilometers. That matches the asteroid belt well. The streaming instability produces predominantly prograde planetesimal binaries. That's in really good agreement with both binaries and contact binaries in the Kuiper belt. Then I went on to talk about pebble accretion. Pebble accretion is a very efficient mechanism to grow the cores of gas giant planets despite the migration. Pebble accretion can outperform the migration. And then I wanted to say that the pebble flux can then determine whether the inner disk forms super Earth or whether it forms terrestrial planets. And sort of my overall take-home message from this lecture is that the migration of pebbles and planets are two really important physical processes that shape the diversity of planetary systems. And with that, I'd like to thank you for your attention and take any questions.
Thank you, Anders, for keeping time excellently. This has been really, really good. I didn't even need to give you warning. That's fantastic. We have several minutes for questions. We start right away with the questions by Paul Macmillan. Sorry if you see me move, it's just because I'm using two screens to see better, so you'll see me move on the other side. So the question says, can your Venus, Earth, Mars model also follow for the existence or explain the formation of Mercury?
No, it cannot. It's a very good question from Paul. Thank you, Paul. No, it cannot form the Mercury. There is an issue with Mercury. Mercury is, in an abundance way, weird. It has dominated by a very massive iron core. It's also too small for our pebble accretion growth tracks. What we think happens is that Mercury formed at an elevated temperature, maybe at 800 to 1,000 Kelvin, where iron starts to become in vapor form. This iron could then diffuse out and make iron nugget pellets that would make a lot of planetesimals made out of iron that would make Mercury maybe in a few 100,000 years. It's very, very fast because it's so close to the star also. So we have to treat Mercury differently, but we think it makes sense because Mercury is also of a very different composition than Earth, Venus, and Mars.
All right, thank you. The other question comes from Matthew Burney. Hi, Anders. Can outflows jets near the centers of the disk affect the planet formation process?
It certainly can. It's a very good question. That's something we are starting to include now, although it's not well understood yet how disk winds and outflows and jets work together. An important thing is actually, I can go back to my Mercury problem. One problem is if you put Mercury to form at point something AU, 0.5, 0.4, 0.3 AU, then it grows so fast that it will actually grow up to a super Earth. If we were not careful, we have an iron super Earth in there, and which we don't. So one thing that might have happened is that it formed fast within the first 100,000 years, and then there were winds and outflows that were dissipating away the inner part of the protoplanetaries very, very quickly. So that Mercury very, very quickly became stranded interior of the main disk, so to say. So I think it can certainly affect out to a few AU, and we would like to include more of these effects in the future.
Okay, thank you. Any other questions? Last call for questions. We still have, in principle, time for a couple. If questions will come up from the audience. Not, I'd like to remind you again that if they come later, they can go in the Slack. So we have a question from Per Björken. I apologize for mispronouncing the name, Björkeli. Nice talk, Anders. Can you say something about the size distribution of pebbles and how it affects the accretion process?
It affects a lot, unfortunately. It's rather unknown. Of course, if we have larger pebbles, what happens is both that their accretion radius increases so that they can accrete from a larger distance from the planet. Secondly, they sediment more to the midplane of the disk, which makes the pebble density higher. So it will affect a lot. One thing I would say about both pebble accretion and streaming stability is a lot of our input parameters, like the pebble size and the disk structure and so on, are based on observables. Whenever we can, we base them on observables. And one observable, for example, all this fantastic work done with ALMA and with VLA, and I know you is also, you're also interested in these kind of questions. One work is to infer the pebble size from observations of protoplanetary disk. And one can sort of look at the spectral energy distribution out in the millimeter centimeter wavelengths and see how that compares to the wavelength of the light and so on. And then people infer typically between 100 microns and 1 centimeter size pebbles, I would say. You want to put really, really broad bands on it. And then we as theorists can sort of play around in all these regimes here. What I normally do is I take millimeter sizes. That seems to work well. 100 microns gets a bit harder in the inner disk, better on the outer disk. 1 centimeter works like a dream everywhere, but the pebbles drift so fast that you lose them also. So we can sort of take inspiration from observations, and then we can play around with the parameter regime, and we can find different effects and different choices of this pebble size. But overall, we still find pebble accretion to be very efficient.
Okay. One question from Jacques Kluska. Very nice talk. What observations of the inner protoplanetary disks would like to obtain to further constrain these planet formation scenarios?
That is a fantastic question. Again, I think we would like to know, we'd like to know everything. We'd like to know the gas density, like the dust density. We'd like to know the dust size. We'd like to know if winds are driving a depletion of the disk early on. We'd like to know if there's more water inside of the water ice line, if there's more iron inside of the iron condensation, and so on. And I think ALMA has been great, and BLA at kind of probing 10 AU and beyond. But whatever we could know in the 5 AU and below, 1 AU and below region in the future would just help us a lot in understanding two-state planet formation.
All right, there is another question which has been uploaded by several people, by Jia Bao Tuong Le. Is there any mechanism that drive the formation of atmosphere of terrestrial planets, as we saw in the case of the Earth and Venus?
That's actually what I'm working on now, since I'm working in an institute now where there's a lot of knowledge about cosmochemistry and geochemistry. I'm actually working now on an outgassing model, where we work on seeing what kind of molecules come out of these planets formed by pebble accretion. And I would say it looks really promising. I think there's a very important difference between the classical terrestrial planet formation, where the Earth forms by planetesimals, and then pebble accretion. That is, with pebble accretion, the volatiles come in with pebbles. Normally we think of the Earth oceans coming in with an icy asteroid or two or a handful of them. But actually, when it comes in with pebbles instead, there's an interesting effect that as the pebble moves through the envelope of the planet, it heats up, and then the volatiles can become thermally processed. It means that around 200 Kelvin, the ice turns into water vapor, and then it runs back into the disk. And later on, you will also process nitrogen, noble gases, and a lot of things. And you can actually then see what makes it down to the surface. And what I get out of that is that there's a pretty good budget of all these volatiles that fits the measurements, the geochemical measurements well. There's a specific thing that's very important here. That is that Venus, Earth, and Mars will get the same amount of volatiles, since they're created from the same pebbles. And that's very different from the classical terrestrial planet formation, where it's random. It's stochastic, whether Venus, Earth, and Mars happen to collide with an icy asteroid or not. So it's work in progress, but I think the most important take from the message from that is that with pebble accretion, all terrestrial planets get the same volatile budget to start with.
All right, you have two last questions. We're going to ask them quickly, and you're going to address them both quickly, and you have lots of questions. So by Bringfried Steklum, what fraction of pebbles end up in the star?
Very high, 95% or higher.
Okay, very quick answer. Final question, Kundam Kadam. What's the characteristic mass of the 100-kilometer planetesimals? And thank you for the nice talk. That's what he says.
I don't know, it's like 10 to minus 6 or 10 to minus 7 Earth masses, I believe. So we must be down at 10 to 17, 10 to 18 kilograms. That's sort of the typical planetesimal mass, yeah.
All right, thank you, Anders, for the great talk and for being so efficient in answering so many questions. And let's move to our next speaker. That is Samaya Nissanke, who is the spokesperson for GRAPPA and a professor at GRAPPA, Center of Excellence in Gravitational and Astroparticle Physics at the University of Amsterdam. She's also joint faculty member at the Anton Pannonek Institute and the Institute for High Energy Physics, also at the University of Amsterdam. Today, she will talk about new perspective onto the universe in the era of multi-messenger astronomy. Floor is yours.
Thanks very much, Sarah. Can you see my slides?
Perfectly, and hear you perfectly.
Perfect, thank you. So good afternoon. So I'd really like to thank the organizers for inviting me to talk about this rapidly exploding and now observationally driven field of multi-messenger astronomy, where we're seeing diverse fields such as general relativity, computational and statistical astrophysics, cosmology, and transient astronomy all converge together to allow us to make this tremendous advance that we're seeing in strong field gravity astrophysics. So I'll be talking about the work and the results done in large gravitational wave and electromagnetic collaborations that I'm part of, as well as work done by members of my group in Amsterdam. And to begin with, it's really important to remind ourselves that this transformation 5 years ago was really made possible by the incredible instrumentation and engineering advances of ground-based gravitational wave detectors, work that took several decades. Now, during the first science run, the 2 LIGO detectors in the US measured 3 binary black hole mergers, resulting in both the first direct detection of gravitational waves, as well as the observation of pairs of black holes actually merging. So shown here is a schema where the vertical axis shows the masses, solar masses, and the blue bubbles that you see represent the progenitor and the final black holes observed in gravitational waves. And shown by the purple and the yellow bubbles are the previously inferred black hole and neutron masses from X-ray and radio observations. And I remind you that that first event, dubbed GW 150914 from the dates of the observation, released 3 solar masses of energy in 0.2 seconds. It was the most luminous event that we'd observed at that time in the universe. Now, since then, thanks to instrumental upgrades during the second science run in 2017, we saw the European-based Virgo detector come online and the discovery of a further 7 new binary black hole mergers, as well as the discovery of this game-changing first binary neutron star merger, GW 170817, that was observed both in gravitational waves and in every part of the electromagnetic spectrum. And what made this so spectacular was observing the electromagnetic emission that was predicted from these delayed matter outflows from the merger of the 2 compact objects, where at least one of the objects has matter. And so this remarkable discovery has allowed for several firsts in astronomy. The first time we could actually pinpoint a gravitational wave event in the sky, the first kilonova discovery in astrophysical sites of our process elements, and the first association of a short gamma ray burst with a binary neutron star, as well as the first Hubble constant constraint with gravitational wave standard sirens. Now, moreover, in 2019, thanks to further instrumental upgrades, increasing the detector sensitivity by a factor of 1.5 or more, we now have at least 50 compact object mergers, as you can see. And of course, an hour ago, we just announced the 2 new neutron star black hole mergers with masses 9 and 1.9 solar masses and 5.7 and 1.5 solar masses from the second half of the third science run, which you can read about in this paper and find out more from the LIGO Virgo CAGRA collaboration webinar in detail on Thursday. So, there are several things I would really like to stress. Number one, that we're actually uncovering this diversity in the fundamental properties, such as the masses and the spins of black holes and neutron stars, which are indicating a broad distribution of masses, with some systems actually showing some asymmetry in their masses. And then secondly, there are several open questions that remain as to the nature of the remnant, as well as what are the actual progenitors of our neutron star mergers, and the existence of various mass gaps between the neutron star and black hole, as well as the pair instability mass gap for black holes above 65 solar masses. And I'd also like to stress that there are several independent analyses which are using open data. I've listed some of the papers at the bottom, which are revealing other interesting candidates. Now, for the rest of this talk, I'm going to focus on these three main characters to really to outline the challenges and the tasks ahead as I see them for the community at large. So number one, GW 170817, the only confirmed gravitational wave and electromagnetic event observed so far. Secondly, GW 190425, the second binary neutron star merger with a total mass of 3.4 solar masses, however, no electromagnetic counterpart and a low signal to noise ratio detection. And 190814, which was the most asymmetric binary that we'd seen so far in 2019 with the smallest localization, the first alert suggesting it was a black hole. Okay, so and really just to stress that gravitational wave and multi-messenger measurements and observations are really impacting a diverse array of fields in astronomy and physics. Thousands of papers have been written about GW 170817. I'm only going to focus on a couple of aspects in this talk in the interest of time, but really just to stress really the plethora of just exciting new fields that are emerging. Now, taking a step back, what are gravitational waves? Well, they're perturbations in the fabric of space-time that travel at the speed of light. Our observable in gravitational wave astronomy is the dimensionless time-varying gravitational wave strain, this h of t, which has a 1 over distance to the source dependence. This is critical when we're using these as distance measures for cosmology. They're coherent. They essentially have two polarizations, so they act as tidal transverse waves. And indeed, this is how Michelson-Fabry-Perot interferometers on the ground actually measure a linear combination of these two polarizations as a gravitational wave passes through this tidal stretching and squeezing. And we now have a worldwide network of operational detectors, including the two LIGO detectors in the US, the Virgo detector in Italy, and the CAGRA detector in Japan, with the much anticipated LIGO India hopefully joining the network in 2026. Now, within the frequency band of the detectors, the most numerous observable objects that we're observing are compact object mergers. But in order to actually extract source information, we rely on accurate models of what this expected wave stream, we call this the waveform, looks like. So broadly speaking, the waveform comprises these three phases, the in-spiral, the merger, and the post-merger, which correspond to different phases in the final stages of the binary lifetime as it's emitting gravitational radiation. Now, the merger is modeled using the post-Newtonian approximation. It's driven by this so-called chirp mass, a combination of the two masses. It appears at the Newtonian order in the amplitude, as well as in the phase. And parameters such as the reduced mass, the spin orbit, the spin-spin, and the tidal deformability of the neutron star, for example, will appear at increasing higher order in the phase of the waveform and can cause beating and modulation of the waveform, in particular for asymmetric systems. And this impacts how well we can actually retrieve these parameters from the wave strain. Now, on the other hand, the merger itself requires numerical relativity, where one has to actually directly solve Einstein's field equations in these dynamically strongly curved spacetimes. And finally, the post-merger describes the settling down of the final remnant of the merger. Now, what I'd really like to stress is that the detector sensitivity is more sensitive to a particular epoch of the waveform that depends on different masses. So for tens of solar mass binary black holes, we're essentially observing tens of cycles of the merger phase that lasts a fraction of a second to a second duration. On the other hand, for low mass neutron star black hole events, we see thousands of orbits of the in-spiral. Okay, and at the moment, post-merger signatures are outside the current sensitivity band of a few kilohertz. So one of the big tasks facing the community is really to input more physics into these gravitational waveforms, in particular for neutron star black hole systems. Now, with these waveforms in hand, one can then actually cross-correlate your detector output with template banks of your waveforms, 10 to the 5, 10 to the 6, to detect and then to actually infer and extract the parameters using random stochastic sampling techniques such as MCMC or nested sampling. And we can extract the following parameters. So the redshifted masses, the spins, the tidal deformability, these appear in the phase of the waveform, and then geometric properties such as the inclination angle, the source position on the sky, the luminosity distance. These appear in the amplitude of the signal. And strong degeneracies really exist, so we sometimes have quite poor constraints, and indeed electromagnetic information can help to break these degeneracies. And so typically the inference can take 1 day to several weeks to months time scale. And of course, for electromagnetic follow-up, we really require faster analysis. So a lot of effort now is going into really speeding up really the inference using machine learning techniques. So to give an example of how well we can actually retrieve the parameters, I'm showing the 2D PDFs for the masses of the heavier object and the lighter object in GW 170817, where this narrow banana sweeps out this line of constant chirp mass that we were able to measure in 1 part in 1,000. And the red and blue curves show the mass contours if one assumes a dimensionless spin in the Z component of the objects of less than 0.85 or 0.05 respectively. Okay, really highlighting this degeneracy I was talking about between mass ratio and spins in the in spiral. And it was really this figure or these measurements that allowed us to conclude that the progenitor was actually a pair of 2 binary neutron stars because of the consistency with the galactic binary pulsar mass distribution. Now, if we turn to GW 190425, shown on the right-hand panel, with a much weaker signal to noise ratio of 12.9, you can see the banana is much thicker as expected. And relaxing the spin assumption, the mass of the heavier object ranges from 1.12 to 2.52 solar masses. And this really begs the question, was this heavier object really a neutron star or a black hole? I'll return to this question and ask whether electromagnetic observations may help in the future. Now, for multi-messenger astronomy, how well gravitational waves alone can localize the source is critical for following up with other telescopes and instruments. Now, gravitational wave interferometers themselves are quadrupolar, they're all sky antennas, they have very poor angular sky resolution, and one must rely on triangulation of the signal of times of arrival, as well as some information of the quadrupole antenna function. Now for GW 170817, along with a distance error of 40 plus or minus 10 megaparsecs, and the sky localization of 30 square degrees, this was sent out at 5 and 10.5 hours after the merger, and targeting essentially the brightest or the most massive galaxies in the gravitational wave volume, resulted in this discovery of 17.3 magnitudes of a bright blue flash at 10.8 hours that was discovered in the galaxy NGC 4993. You can see this by the red arrow on the right-hand panel. And this was discovered by the SWOPE telescope in Las Campanas in Chile. And impressively, this first reported bright flash ended up really being the real deal, the neutron star binary. And this confirmation, I'd like to stress, really relied on the subsequent photometric and spectroscopic follow-up in the next days, really indicating it's one of its kind nature. And so we're finding that this is not the case for weaker gravitational wave signal events. And really we are faced with this challenge of characterizing other astrophysical transients and variables, really looking for the needle in the haystack of the transient sky. So one may ask, why have we not detected other electromagnetic counterparts for the events that involving a neutron star in 2019? Did we just get lucky? Well, let's consider what happened in the public alert era of 2019. There were 56 non-retracted alerts sent out, 8 were binary neutron star alerts, and 7 were neutron star black hole alerts. Now for GW 190425, which was classified as a binary neutron star immediately, the gravitational wave sky position was a quarter of the sky and the distance was 4 times greater than GW 170817. Okay, so the great challenge here was the sky area, because this was detected only in the LIGO-Livingston detector. Unfortunately, we do have new facilities such as the Zwicky Transient Facility on Mount Palomar with its field of view of 47 square degrees, which was able to actually cover the event, the initial sky map, by about 40%. Now, on the other hand, for GW 190814, the sky position was in fact only 20 square degrees, but the distance this time was 6 times that of GW 170817. So here, the distance itself was a challenge, but with its small areas, many telescopes were able to actually focus on depth and long exposure times. Unfortunately for this system, and it's still, the jury is out whether it's a binary black hole or a neutron star black hole, but if it was a neutron star black hole, the asymmetric mass ratio would have been that the neutron star would have been swallowed whole by the black hole without any matter outflows. But it was certainly a very exciting August evening that I remember. Now coming up to the actual identification, well, what's the state of the art? Well, I'm showing an example from the Zwicky Transient Facility that followed up 13 gravitational wave event localizations in 2019, and they had over 2 million alerts. Now with machine learning as well as human vetting, they were able to whittle this down to 127 candidates that were sent out to the community, and follow-up spectroscopy and photometry, as well as further analysis with revised gravitational wave information, as well as archival catalogs. They were able to actually reduce this really to 0 kilonova candidates, which sounds a bit bleak, but indeed, even with this information, it was possible to actually put interesting limits on the kilonova luminosity function. Now let's return to GW 170817. Again, I think what really made this event such a celebration was just the sheer amount of data obtained and the community involved in following up the event. Over 100 instruments, 80 groups in the world using a slew of ground and space-based telescopes. And the multi-messenger discovery paper, which I was heavily involved with, encompassed 3,000 co-authors. I really think the tremendous community spirit in following up this first binary neutron star was simply beautiful. Now, really just to stress that the different measurements in different frequency bands and timescales allow us and are necessary to probe the physics during the post-merger evolution. And this figure encapsulates, I think, the full panchromatic beauty of these first few years of observations that are still ongoing. And so broadly speaking, there are these 2 classes of data, the UVOIR in the first weeks, and then the radio and X-ray measurements associated on the months to years timescale. Now, for me, also what made this huge data set of observations so impressive was that at 0th order, they agreed with the prediction that there should be 2 types of matter outflows responsible for EM counterparts. First, the so-called kilonova or macronova, a rapid neutron capture nucleosynthesis powered transient emitting thermally in the UVOIR from hours to days to weeks after the gravitational wave event. And this can occur due to initially neutron-rich outflows happening from tidal tails, disk winds, as well as core bounce heating as the two neutron stars slam into each other. And the second is the short gamma ray burst and its afterglow arising from accretion onto some centrifugally supported accretion disk, which is powering a relativistic jet. And of course, here the emission depends on the observer's angle with respect to the barrel of the jet. So therefore, from the electromagnetic counterparts, we are measuring orthogonal quantities such as the redshift, the outflow properties and composition, the energetics, the environment, as well as the inclination angle. And I'm just going to show two examples from the plethora of beautiful results that have come out. And so an example of the composition measurements that you can make is demonstrated by this really breathtaking movie compiled from snapshots of actual spectrum from ESO's VLT that show this initially blue featureless spectrum consistent with a cooling black body rapidly evolved from blue to red on the week time scale with the appearance of these broad absorption features, which are indicative of the spectral fingerprints built from our process elements. Okay, so this really sort of emphasized that this was a transient unlike we'd ever seen. Now, another beautiful result was the VLBI met constraints on the proper motion of the centroid of the source that were taken at two different epochs within the year later after the event, which suggested that the jet actually had some radial or angular structure, and with the X-ray and radio light curve indicating that the inclination angle to the binary was 15 to 25 degrees. And actually this information was critical in improving the Hubble constant measurement that was possible from GW 170817, essentially breaking the degeneracy between the distance and inclination angle that I mentioned occurs in gravitational waves. So it improved the H0 measurement by a factor of 2 or more, but of course the caveat is astrophysical modeling of the jet. So today there are several open questions that remain. What's the central engine of the jet? What's the origin of the blue kilonova? And we have really entered this new field, which several groups in the world, including my own, are working on, which is to combine and interpret all these measurements in a comprehensive and systematic framework. This is non-trivial due to the large numbers of parameters involved, the yet to be identified degeneracies between the parameters, as well as the systematic modeling errors in these orthogonal data sets. So as an example, I will quickly return. And so this is our next big task. And so as an example, I'm going to quickly return to this question of the progenitor nature of GW 190425. And if we had measured electromagnetic information, would this have helped for this very low signal to noise ratio binary? So on the left-hand side, we show a suite of model light curves from different groups. And we look at a variety of cases where we assume electromagnetic modeling uncertainties are improved, as well as photometric measurements for this particularly sort of bad case or worst case scenario. Shown here on the right are the 2D PDFs for the mass ratio, the tidal deformability, and the black hole spin, with the gravitational wave alone shown in gray and the gravitational wave plus the optical data shown in red. And my PhD student, Hert Reimakers, will discuss his end-to-end multi-messenger analysis and infrastructure in tomorrow's session. Where are the black hole neutron star binaries? Now, a critical ingredient for this analysis, as well as for electromagnetic follow-up, are the semi-analytical formulae that relate the progenitor properties to the initial outflow properties. Now, in the case for neutron star black holes, we have calibrated these formulae to 75 numerical relativity simulations, as shown in this phase space plot of the black hole spin on the vertical axis, as well as the tidal deformability on the x-axis. And the different panels represent different mass ratios of the neutron star black hole. And you can see that sort of the mass, remaining mass are outside the remnant, which is shown by the color bar, as well as the contours. really, there's only a certain sweet spot in this phase space, which actually allows for matter outflows to happen, essentially for high black hole spins, low mass ratios of neutron star black holes, and relatively stiffer equations of state. So my last
5 minutes.
Yes, in my last few minutes, I'm just going to end with the perspectives. Okay, so we are really entering this era where gravitational wave detections are and alerts are becoming routine. So what does this mean? So for future electromagnetic follow-up, I think we must continue to be prepared for a diversity of electromagnetic counterparts that really depend critically on the progenitor and remnant. You know, GW 1708-17 may not be just a vanilla case for neutron star binaries and the electromagnetic counterparts. Secondly, in order to actually analyze carefully joint data sets, we really must continue our efforts to build a coherent model of the in-spiral merger and microphysics plus the radiation transport from numerical relativity, hydrodynamic codes, and radiation transport codes that model these outflows and can really reach this challenge of dealing with the orders of magnitude variation in both the length and the time scales. Thirdly, to go after the early UV emission within 8 hours of the merger, we actually missed this emission. The first optical counterpart was seen at 10.5 hours. To really understand the origin of the early blue kilonova emission, and several small satellites, such as the NASA Dorado satellite that my group and I are part of the science team, are just going through phase A with the dedicated goal to actually follow up gravitational wave mergers. Then fourthly, we have already moved from this individual objects to statistics era. So shown here the cumulative events or candidates as a function of time. And I remind you that we have still not released all the events that were seen in the final second half of the third science run. And this means that in the next 4 years, we can really anticipate to have several to tens of neutron star, neutron star, neutron star black hole mergers per year. But fortuitously, we also have a whole plethora of new telescopes and astroparticle facilities coming online, such as the Vera Rubin Observatory and the SKA precursors, as we've heard. Now, to zoom in on the EM follow-up challenges, this plot quickly just shows that as the rate substantially increases, our network of detectors will also increase with LIGO India. We expect smaller areas and larger depths. And shown in these cumulative detection rate plots as a function of the sky area and the distance, we can expect several to tens of these mergers being localized within 100 square degrees, as well as several golden, and by golden, I'm talking about those within 200 megaparsecs being visible. And finally, I'm going to just end with saying that all of this, what we're seeing in the 2020s, is really in some sense an anticipation to the possible construction in Europe of the Einstein telescope, a facility that really keeps me up at night. And so shown in this plot is the redshift as a function of the total source frame mass, and the detection range of the Einstein telescope is shown in green. So essentially we'll be able to detect all the observable neutron star, and neutron star black hole mergers in the universe, tens of thousands per year. And so we are already having to think about this radical transformation of what multi-messenger astronomy will mean there in terms of large-scale structure, extragalactic astronomy. And finally, just to end with my final slide, I have really talked about only the high end of the frequency space that will be probed, or that is currently being probed by different experiments, as well as upcoming missions such as the LISA satellite. And there will be, within this frequency, within these decades frequency range, there'll be many events that will also have gravitational wave and electromagnetic emission. And so really just to highlight and to end on this excitement that I think we are discovering, and we have really opened a new window onto the universe. Thank you.
Thank you, Samaya. So you already have 2 questions, not surprisingly, given the fascinating nature of the talk. So the first question is from Rahul Srinivasan. What were the EM conclusions on today's 2 NS black hole announcement?
Thank you for that question. So yes, so we, as you may have heard, there were no electromagnetic counterparts actually detected for this event. So I'm just going, yes, so I'm showing basically the sky errors for the 2 events that were mentioned. Now, the first event actually had a sky error of 7,200 square degrees, because once again, it was detected only by LIGO Livingston. Okay, so and so incredibly large, whereas the second event actually had a sky error of 600 square degrees. And shown here are actually the follow-up, where I think 48 and 22% of the sky area was actually covered. This is shown in this paper by Anand and Coughlin, probing actually the sort of the relevant depths. The event actually happened at a few hundred megaparsecs, so it was relatively very far, but it was interesting in the sense that limits and interesting limits were actually were actually put on the possible kilonova emission. Now, in terms of the actual models that looking at neutron star black hole systems, for the parameters at the moment, it was shown that the ejected mass would be about 10 to the -6 or less for the particular parameters, even though the mass ratio was relatively low here, because of this sweet spot of the phase space I mentioned between neutron star black holes. So we don't, number one, the systems, from a theoretical point of view, we didn't expect electromagnetic emission, and secondly, from the observational point of view, quite a lot of limits, or I think very admirable limits were put on this system, on these 2 systems.
So one more question. We're already a little bit over time, but we have time at least for this question. By Jiqiang Yan, what is the distance redshift of the closest GW event from us? Can we tell?
Yes, so I think it's this 40 megaparsec event, GW 170817, that was seen. Yes, so that was really, I mean, it had a signal to noise ratio of 32. So it really was, an ultra golden binary in the sense that it was just so close to us. Yes, so that really was, and most of the sources that we are seeing at the moment, the medium distance is about 250 megaparsecs for binary neutron star candidates and a few hundred megaparsecs for neutron star black hole candidates. So much further out.
All right, thank you. This is all the time we have for today, but I remind all attendees, they want to ask questions to all the speakers from today, they can do so in the Slack. I would like to thank again all the speakers for today for their excellent talks, to congratulate again Mirjana and Catherine on their prizes. And I invite you to join some of the afternoon sessions and enjoy the rest of the meeting. Thank you very much for your participation.